I'm Jaime, I'm at CVSSP in the University of Surrey, and today I'm going to be talking about some of the recent work we did on generic dense feature learning, which, as Christian said, was presented at CVPR a few weeks ago. Maybe. Okay, decided to skip a few slides. Cool. So, as you might expect, SAND is an acronym. It stands for Scale Adaptive Neural Dense Features. At its core, it's a method for dense feature extraction, meaning that for every single point in the image, you get an n-dimensional feature vector to represent it. What we show is that instead of just doing, for example, random sampling or hard negative mining in order to get the negatives, if you restrict the area that you're allowed to sample those negatives from, you can change the properties that the feature learns, which might be good for different tasks. So, for example, here in these images, the only thing that's changed in the training process is what set of negatives it was given to compare against. We can then take this one step further and combine multiple of these negative mining strategies together in what we call hierarchical context aggregation. And then we show how we can achieve better or comparable performance in a wide range of computer vision tasks. In this case, disparity estimation, semantic segmentation, self-localization, and Slang. And of course, there's code available at the link here. So feature extraction is one of the core components of computer vision. So it's no surprise that there's been quite a lot of work done in this area. So I'm guessing that most people here will be familiar with traditional handcrafted features like SIFT or SURF, and these features are very good and they're still used nowadays, but they haven't really seen much use in cases such as deep learning, for example. Next, we have holistic image representations, where the idea is that instead we have one single feature vector that represents the whole image. As such, these features tend to be used more for tasks such as image retrieval or person grid identification. And this is where things like contrastive loss or triplet loss kind of come from. As an intermediate step, we have the learning of feature detection and description, where, for example, Salty et al. Treat key point detection as a binary classification task, whereas Georgiakis et al. Jointly learn features and key points. And then also from CVPR, we have D2Net, which opts for a describe and then detect approach, meaning that you learn dense features, but then use non-maximum suppression to select key points of interest. And then more related to what I'm talking about now is other dense feature representations, such as Smith et al., who introduced a pixel-wise version of the contrastive loss, and then also from CVPR, SDCNet, which in this case focuses more on the design of the architecture based on stacked dilated convolutions rather than the actual training process. So quick recap. So the idea is that based on different negative mining strategies, we can learn features with different properties, which we can then reapply to multiple tasks without having to modify them too much. So again, at the core, we have the feature extraction, and the idea here is that we're providing a dense feature map, meaning that if your input to the network is a height by width by 3 image, your output will be a height by width by n dimensional feature map. So in order to do this, we use a fully convolutional network, where instead the final stage of the encoder is replaced with a spatial pooling pyramid with 4 different levels, which kind of helps you to aggregate that information at different scales. So in order to actually train the network, we use ground truth correspondences between images, which tell you which pixels in one image match to the pixels in another image, and we use a pixel-wise contrastive loss. And the same as with traditional contrastive loss, the main idea behind it is that similar features should be close together in that feature space, whereas this similar example should be separated by at least a set margin. And due to the nature of the data, this means that the set of positive samples is fixed by your ground truth. Each pixel only has one corresponding pixel in the other image, but leaves an open question about what the negative samples are. So when you think about it, each correspondence has pretty much a whole image worth of potential negative correspondences. And it's obviously infeasible to actually use this for every single correspondence. So in the base case, what you can do is just randomly sample from the image, or do hard negative mining. Instead, we propose a spatial negative mining approach where you can define the maximum and the minimum distance that you're allowed to draw these negatives from. So, for example, in the left image here, we have the local approach where you're restricting that mining range to a 25 pixel circle around the original correspondence. So this is defining where you require that feature to be unique. It only needs to be unique in that specific patch, and it doesn't really care about what else is in the rest of the image. If we want to learn more complicated features, what we can instead do is combine multiple of these negative mining approaches together and train them simultaneously. In this case, what I mean by splitting is that, for example, if we have a 32-dimensional feature, we can take the first 16 dimensions, train them with a set of global negatives, and take the last 16 dimensions and train them with the local set of negatives, and then combine the feature maps again. And this is what we call hierarchical context aggregation. So in order to get some idea of what the network is actually learning, we can visualize the features by projecting them via PCA. And here what we can see is that, for example, the global features, which are shown on the top, tend to learn more semantically similar objects. So, for example, the road or the buildings on the side, the cars. Meanwhile, the network that was trained with only that local patch tends to focus a lot more on things like the edges and the textures of the image. And again, this makes sense because you're requiring it to be discriminative in that small patch rather than the whole of the image. We train using only a subset of Kittier geometry 0, but again, it's worth remembering that for each pair of images, you have 15 to 20,000 correspondences, and for each of those correspondences, you can choose 10 or 15 negative samples to train. So in this case, we look at the distribution of distances between the features, where, for example, mu positive is the average distance between corresponding pixels, so correct matches, which want to be as low as possible, and meanwhile mu negative is the average distance between non-corresponding pixels, which want to be as large as possible. So we can see, as we would expect, that when you train with the global mining approach, you get better global performance. When you train with local, you get a better local performance, which again is that 25 pixel radius around the original match. Meanwhile, with the hierarchical approach, it provides kind of a compromise between the global and local, where you're slightly boosting performance in each of those, and it's also maximizing that distance between the negative samples. It's also worth noting that this top block is done with 3-dimensional features, so very compact, and it is still outperforming all in that kitty, in the rest of that kitty sequence. So now that we have these features, the question is, where can we apply them? And in this case, we want to show that you can use them in a relatively wide range of computer vision tasks. So we opt for disparity estimation, semantic segmentation, self-localization, and Slang. And generally, the objective here is to introduce SAM into an already existing system and show that with little effort and little no additional training, you can improve the performance. So disparity estimation, for example, this tends to focus more on narrow baseline matching, and we do this in a further end-to-end deep learning fashion, where the idea is that you take a PSNet, so a disparity estimation network, and simply replace the input image to the network with the learned dense feature representation from SAND. And we can see, for example, here in the highlighted regions, how by including these features, we can improve the robustness in complicated areas such as the transparent windows of the car. And in terms of semantic segmentation, we use a similar approach to disparity, where we use a cost matching volume and replace the input to the network with the learned feature representation. So again, it's a case where we're doing further deep learning processing. In terms of self-localization, we're replacing the input image to PoseNet, and self-localization in this case tends to focus more on that wide baseline matching and being able to detect revisitations. it is worth remembering that, so in this case, PODNet is being evaluated on the Cambridge landmarks dataset, whereas the features were again still only trained exclusively on that small part of Kitty. And yet, without any additional fine-tuning, we can already achieve comparable performance to the baseline. And if we additionally fine-tune the features at a lower learning rate for a shorter amount of time, we can increase that performance as well. And then finally, perhaps the more interesting task is SLAM. And in this case, the features serve as a direct drop-in replacement for all features. No additional training, no further processing. You can use the same key point detector, nearest neighbor matcher, and you just get that increased performance. And SLAM is interesting because you need local features that you can match from frame to frame, but you also need features that are global enough to detect that revisitation and perform loop closure. Funnily enough, what we find is that if you use only the local variants of the features, you can get better visual odometry performance, but your loop closure